Can somebody confirm me that my screen is visible?
Yes, it is visible.
Thank you. So it's time. So shall we start, or shall we wait for some more time for people? Okay, then let me introduce myself. I am Dinesh Kumar Singha. I am a PMRF fellow from University of Hyderabad. So I'll be taking this tutorial class every Saturday from 3 to 5, and the course is Introduction to Statistical Mechanics. So I think we should start. So I'll be taking tutorial. So let's come to the first question. As sir has taught you in first week, like about isolated system. Isolated system means uh, no heat will come out or in from this system, or no particle will come in or out from this system. So the question is, entropy of a isolated system is always dash and becomes a dash at the equilibrium state. Equilibrium state means a microstate which is not changing over a period of time. As time progress, this state is not evolving with time. It's as it is. So it's called a equilibrium state. So for equilibrium state, for an isolated system, and the entropy always increases, and it becomes maximum at a state of equilibrium. As sir has taught you, if the steps are limited, like he has taught you in staircase problem, like if the stairs are countable, they are limited, and we have limited number of people, then the entropy function will look like this. This is entropy. This is some variable, you say it what to say, number of steps. Then at equilibrium, the middle point, it does not need to be 0 at this origin point. At equilibrium, so this entropy will be maximum, and at highest occupancy, this entropy again goes to 0. But this is not the case for infinite staircase. Like if there are infinite stairs, then this entropy can go linearly. Entropy will increase always, and it won't come to 0. So for the isolated system, and entropy always will increase, and it will be maximum to the state of equilibrium, as we saw. It will always increase, then it will be maximum, then it will decrease as we progress with steps. So So the first question's answer is the entropy will increase and it becomes maximum at the equilibrium. Let's come to the second question. Not correct. Answer should be B. Right. So, which of the following statement is true? A given macrostate typically correspond to a huge number of microstate. As you might be knowing, a macrostate is always a ensemble of many microstates, like a box containing n number of particles with some energies, like energies goes from 1, 2, 3, 4, 5. So these n number of particles, they can occupy anywhere. Any arrangement could be possible. Like in first energy level, there could be some n1 number of particles. In second energy level, there could be n2 number of particles, and so on. So we can this n1, n2, n3, these can vary. Means they are not fixed. There are ways we can arrange them. So a macrostate is always a means it comprises of microstates, and these microstates can be arranged in a huge manner. Means they can be arranged in any manner. So this arrangement, collection of arrangements, we call a macrostate. So the first statement is true. Second statement is a given macrostate always has exactly one microstate. As we have seen, it's not true. It comprises many microstates, so it's not true. Then coming to the third case, entropy is a function of microstate of the system. No, it's not true. And from Boltzmann law, we know entropy is a function of a macrostate. Actually, it's a logarithm of number of arrangements. What you can call into lambda. This is the number of ways you can arrange the particles inside a system. So it's a macrostate. They can be arranged anyhow. We don't care. We just want the number of ways they can be arranged. So this is also not true. Different microstates always correspond to different macrostates. That's not true actually, because this is a macrostate which is comprised of many arrangements of these microstates. So there can be any kind of arrangements, but the number of arrangements, that's what we care for a macrostate. So this is also not true. Okay, coming to the third question. From a standard deck of cards, if we have 8 cards and 5 of them are black, calculate the entropy of the system. Sir already solved this problem in his class also, this kind of problem. So let me try this. So in a deck of cards there are 52 cards, out of which 26 are black and 26 are red cards. So what we have? We have 8 cards. So this 8 card can be anything, in some n1 number of black cards and n2 number of red cards. So n1 plus n2 is 8. We have 8 cards. So, but in our question it is given that 5 of them are black cards. So this n1 is 5 we have. So n2 will be 8 minus 5. 3. So we have 3 red cars and 5 black cars. Then calculate the entropy of the system. So we have 26 possible black cards, and out of which 5 are we are having in our hand. So what is the possibility that possible arrangements of this system? Like there are 26 possible black cards, but we have 5 5 black cards. So this can be any number of cards there for each set, and there should be some shapes, some black and I don't know the names, diamonds and spades, something like that. So 13 each, they have shapes, different shapes. So this diamond, this is spade. So these 5 cards can be any of the cards, like it can be a heart, 2, 3, 4, king, or something, queen, or those cards. So what is the possibility? What is the number of arrangements we have? 5 cards out of those 26 cards. So it will be a combination of 26 out of 5. So this will be 26 factorial divided by 26 minus 5 factorial by 5 factorial. This is the combination rule you might be knowing. NCT is n factorial divided by n minus p factorial by p factorial. As we do not care about the order of choosing, so we don't need to take the permutation case. For this permutation function we can define as n factorial divided by n minus p factorial. If we care about the arrangements, that we have 5 cards, how we arrange those 5 cards, then we need to consider this permutation formula. But we do not care about the arrangements, we just need 5 black cards in whatever order, we don't care, but there should be some distinction, so we need this formula. So we have finally this much of arrangement for the black cards. Similarly, we have 26 red cards, out of which 3 are we are having in our hand. So what is the possible arrangement for that? So it will be 26 C3. So that will be 26 factorial divided by 26 minus 3 factorial 3 factorial. So these two are the possible arrangements for the cards we are having in our hand. 8 cards we are having in our hand, so these two are the possible combinations. So total possible combination will be multiplication of this and this. So let's clear this. So total possible choices are 26 C5 into 26 C3. This is the total possible combination. Our master state comprises this number of microstates. So what is the probability? Not probability. What is the entropy? Entropy will be KB ln this microstate. So what will be KB ln of this 26 C5 C3. Then we have to solve this. Okay, KB we can take 1, as we want to calculate in energy unit, we don't want to calculate in temperature unit, so we can take KB to be 1. So what remains? ln of 26C5, 26C3. So this is ln means log base e, right? So ln of this first will be 26 factorial divided by 26 minus 5 is 21 factorial into 5 factorial. Ma'am, I am in class. So then this term will be 26 factorial divided by 26 minus 3 is 23 factorial into 3 factorial. Then this we can solve as ln of 26 factorial we can write as 26 into 25 into 24 into 23 into 22 into 21 factorial. In the denominator we have 21 factorial and we have 5 factorial. 5 factorial we can write as 5 into 4 into 3 into 2 into 1. And similarly for the second case, we can write 26 factorial as 26 into 25 into 24 into 23 factorial, and in the denominator we have 23 factorial and 3 factorial is 3 into 2 into 1. So we see we can cancel this 21 factorial above and below, and here we can cancel 23 factorial. So we have, what do we have? 5 into 4 into 3 into 2 into 1. So we need to cancel the denominator with the numerator. So we can cancel 5 by 25. It will be this will be 5, 4, 6. 4 into 3 into 2 are 24. So these 3 will be cancelled with 24. Here we have 3 into 2, 6, 6, 6, 4 are 24. So what we are left with ln of 26. We have 2 26, so 26 square. Here it is 5. So we have 125, 123, 22, and 1, 4. So you might be needing calculator to calculate this. So when we calculate this, logarithm of this number will come to this 18.95. So the correct answer will be 18.95. Right. So far anyone has any doubt?
Can you explain me the first problem that you have discussed?
Okay. So the question is the entropy of an isolated system is always dash and becomes dash at at the state of equilibrium. So isolated system means, so it is not exchanging heat, or it's neither exchanging the number of particles, right? So it is isolated. So entropy, from the second law of thermodynamics, you know, like entropy always increases. So for isolated system also, if heat is not coming also, they will arrange themselves, the microstate will arrange themselves, like the entropy will always increase up to a equilibrium point, right? This is entropy, and this is number of microstates. Let me write it some k. So the entropy will increase when the equilibrium hits, then this entropy will be saturated. So this will always increase, the entropy will always increase, and it will be maximized at the equilibrium state. Equilibrium state means at this point of time, means at this point this process will not go to the right or to the left, so it will be stationary at this point, and the system will be always like this in all the time after this. As time progresses, like let me say a plus b is going to c plus d, then c plus d always can go to a plus b. So there is a reversibility always. So you can write this as a plus b going to c plus d, or c plus d going to a plus b. So this is the condition of equilibrium, like a and b, they are combining and they are going to c plus d always, and c plus d again combining there and they are going back to a plus b always. So there will be a point where this process will no longer exist, and there will be certain number of a and b and certain number of c plus d. They, after some time, they won't again they won't convert to each other, or you can say like they will convert, but the numbers will always be same. Like if you have two numbers of a and two number of b, they are creating three numbers of c and three numbers of d, or two numbers of c, two numbers of d. A plus b are combining to give c plus d, then simultaneously c plus d is combining and giving a plus b. This process is simultaneous. A plus b is combining and then going to c plus d, simultaneously c plus d is combining and giving a plus b. So effectively their numbers are constant after certain points. Initially there might be four number of a and four number of b, and they are evolving and they are going to c plus d. Initially there are 0 0. So after equilibrium, the situation will be like this. At equilibrium this number will be constant, so at this point this entropy will be maximum. So if we forcefully like you put some catalyst in this process, like if you try to enhance this c plus d process, then this transaction rate from c plus d to a plus b will be higher. Then in that case the entropy will again decrease. But we know, as long as we are not putting any additional catalyst to the system, as the system is isolated, we are not giving any heat, or we are neither exchanging any particles, so this possibility we are discarding. So it will always stay in the equilibrium position. So the entropy will increase and it will be maximized at this point of equilibrium, right? Do you have still any question regarding this?
No, you can proceed.
Okay. So it's clear, right?
Yes.
So coming to question number 4, we have Alice who has 3 black balls and 3 red, sorry, cards actually, who has 3 black cards and 3 red cards in her hand from a standard deck. Standard deck means there will be having 52 cards, 26 black, 26 red cards. Okay. And Bob has 4 black cards and 2 red cards from that standard deck, another set. So who's who is having higher entropy, like whose hand of cards has higher entropy? We need to find Alice system is higher entropy or Bob system is higher entropy. So it's a similar case like the previous question. We need to calculate the entropy twice. So we need to calculate the entropy for Alice and we need to calculate the entropy for Bob. So let's start. So for Alice we have 3 black cards and 3 red cards, and for Bob we have 4 black cards and 2 red cards. So similarly, the choice of black cards for Alice will be 26 C3, and for red card it will be 26 C3. The total microstate, the total combination will be multiplication of these two. So the entropy for Alice will be, I am neglecting this KB and I am writing this state as ln sigma 1. So it will be natural log of 26C3, 26C3. So let's calculate this as it's double. We can write 26C3 whole square. Then we have to just calculate once, then we will square it. So 26C3 we can write 26 factorial divided by 26 minus 3 is 23 factorial, right? 3 factorial. This is whole square and then natural log. Then this will be 26 factorial, we can write 26 into 25 into 24 into 23 factorial. And the denominator we have 23 factorial, and 3 factorial we can write 3 into 2 into 1, and this is whole square and natural log. And we can cancel 23 factorial, and 3 to 6 and 4. We are having effectively ln of 26 into 25 into 4 whole square of this. So do anyone have calculator? You can right now, and can someone calculate and tell me the number? And let me calculate also. So this is 26 into 25 into 4 okay.
15.72.
Yes, right. So this is 15.70. So for Alice, entropy is 15.72. So remember this. Then we have to calculate for Bob also. So total number of microstates for Bob will be 26C4 multiplied with 26C2. So the entropy for Bob will be natural log of 26C4 into 26C2. When we expand this will be 26 into 20. Okay, we will write first in factorial down. So this is 26 factorial divided by 26 minus 4 is 22 factorial and 4 factorial into 26 factorial divided by 26 minus 2, 24 factorial into 2 factorial. Right. Then we can expand this 26 to 25, 24. This part. Four, 23. So this is equal to ln of 26, 25, 24, 23, 22 factorial. So we have 22 factorial in the denominator, and 4 factorial is 4 into 2 into 1. Does anyone have questions? It's 26 equal to 26, 25, 24 factorial. In the numerator we have 24 factorial. So 24, 24 cancels, 22, 22 cancels. Then this is 4, 3, 2, 6, this is 24, 24. So we have 2 factorial means it's only 2 into 1. So 2 we can cancel here. So 30. So effectively we are having 26 into 25 into 13, 23, 25. Can someone calculate this and tell me?
It come around 15.39.
15.39. Are you sure?
Yes.
15 or 18? Let's check again. It's 26, 25, 23, 13. Right. Let me check once. 15.3. Okay. The first one is correct, right? 15.72.
Yes, it's correct.
Okay. So okay then. So Bob's entropy is 15.39 and Alice's entropy is 15.72. So clearly Alice has more entropy. So the answer will be higher entropy is Alice. Right. Coming to the next question. Consider a case where there are 3 steps. 2, 3. In a staircase, all with equal height. So from the ground, this edge, from this point to this edge, from this point to this edge. So from ground, its first one is edge, the second one will be 2 edge, and the third step will be 3 edge, right? Then there are 3 different peoples. There are 3 different peoples. A, B, C. So with equal weights, their weight are equal. W. Weight means mg. You might be familiar with the physics problem. Like when we calculate the potential energy, we used to write this as mgh, right? So mg is W here, so WH. So the potential energy will be WH for this case when the height is h. So how many ways can the potential energy be 8 Wh? It's 1 Wh. How many ways the potential energy can be 8 Wh? So let's do this. So we have 3 shares. I am writing as bars for them. One is h height, second one is 2h height, third one is 3h height, and we have 3 people. We have to arrange them in this 3 staircase. So one possibility is 1 1 1. Each people will be staying in each stair. Then second possibility is in first one there will be 1 people, in second stairs there will be 2 people, and in the third case third stairs and there will be 0 people. Then we can do the reverse also. In first one there will be 2 people, and in the second stair there will be 1 people, in the third there will be 0. Similarly we have to arrange how many combination we can get. See, so I can do like this: 102, 201, or 012, 021. This is 1-2 combination. Then we can put 3 people in any of the stairs. Let's assume in the first stairs I am putting 3 people. Then we can put 3 people in the second stair and 3 people in the third stair. Right. Let's calculate their potential energy. You will be, first one is h height, so they have equal weight W. So first one will be WH. For the second second person is in 2h, so this will be 2WH, and the third person is in height 3h, so for him it will be 3WH. So the total will be 6WH. Right. So this is the first for the first combination. Similarly, for the second case, we can write for 1 people is staying in height h, so it will be WH, and there are 2 people in the second case, second stage. So there are 2 into 2WH. So there are 2 people, no? So that's why 2, and the potential energy in that state is 2WH. So total will be 5WH. So similarly for the third case, we will have 2WH plus 2WH. There are 2 people in WH, so 2WH, and there is 1 person in 2WH, so it will be 4WH. So let me calculate all others. So it will be WH plus 2 into 3WH plus 6, 7WH. For this case, this is 2WH plus 3WH plus 5WH. For this case is 2WH plus 2 into 3WH, 6, 8WH. Similarly, 4WH plus 3WH, 7WH. For this case 3WH. So this will be 3 into 2, 6WH. U will be 3 into 3, 9WH. So we have this many combinations, but there is a catch. These 3 people are different people. They are distinct. They are not identical. So you see, in the first case we are putting each people in every state, so I can rearrange between those states also. Like, let's assume first case is ABC. This is the people name ABC. So we can arrange them differently. If I can bring B to here and A to there, then how many elements will be there for this combination? Can anyone tell me how many ways I can arrange these 3 people in these 3 states? It's 3 factorial. You can manually compute this. Like, I can put A here, and I can arrange between B and C. Like, For the first case, B will be here and C will be here. For the second case, C will be here, B will be here. Means A in first layer. For that, there can be two combinations like between B and C. So for A in first layer, there are two combinations for between B and C. Similarly, for first layer, I can place B in the first layer, and I can arrange between A and B. Let me erase this. Might be creating confusion. Similarly, I can put B here. Then I can arrange between A and C. Like I can put A here in the second stair and C here in the third stair, or I can put C here and A here. So there are two different possibilities for B in first state, B staying in first state. There are two combinations between A and C. Similarly, I can do the same thing for C in the first state. C is the first state, then I can arrange between A and B. So there are two possibilities for C in first state. So in total there are 2 plus 2 plus 2, 6 possibilities of arranging these three people in this combination. So this is 6. Then for these cases, if we get any one of these, then we will find all of these sets. Like their combinations is similar. Let's see. So for the first case, I am putting one people here and two people here. Let's assume I am putting A here and B and C in the second stairs. Or I can do something else. Like I can put B here, then A, C will be there. Then I can put C here, then A and B will be there. Is there any other possibility for this combination? Anyone? This state would be this third stair. This will be empty always. So there are no other possibility I can arrange for this combination. So there are three possible combinations for this case. So this is three possible combination. And for this case also you will see similar case. You will put two people here in the first stairs, then one people in the second stair. You will have three possible combination, and for this also 3, 3, 3, 3. And there are three people coming to these combinations. There's three stairs. You either put A, B, C in the first stair, or you put, there is no other possibility like for this case. Arranging between A, B, C in the first stair does not make any sense. We want to arrange them in the stairs, not in the same stairs. So for this case it will be 1. There is one possibility of arranging between A, B, C in the stairs. So similarly for this case also 1, 1. So these are the possibilities of arranging these three distinct peoples. If they were marbles, so they will be indistinguishable. So we no need to arrange them. Arranging one marble here, two marble here, third marble here does not make any sense. Revolving between them, because they look alike. So there is no need for, if they are marked, but they are people, they are distinct from each other. So you see there are three possible way of arranging this first combination. So
Hello, sir.
yes,
Uh, about marble can be distinguishable.
no, we are taking, I am talking about identical marbles, means they look alike, their shape is same, their color is same. If we consider that, there is,
Okay.
yeah.
Yeah, but Then we think about this these three men.
Hmm.
The weight is the same. That means we can say they are identical.
If they are triplets, like the three peoples, they look alike, means they look the same, then you can you don't have to arrange them, these peoples, in different orders. You just have to take the combinations in the stairs. Because they are very distinct, they look very different, we can arrange between them in the stairs. They will look different, like A in the first state and BC in the second state will be very different case.
Okay.
Okay, you understood, right? Like this will be different.
Yeah. Yes, sir.
Okay. So we have three possibilities for the first case. So the energy, this will be, there will be three possible combinations for this first state. Similarly, there are six possible. Sorry. This three is not for this one. There are six possible ways of arranging this first combination and three possible ways of arranging this combination in these. So there are six uh, 6 WH here, and we need to find 6 where we can find more 6. Here is one. So there are 6 plus 1. Here is 1. So there are total 7 microstates with energy 6 WH. Right. Here is 6 microstates and we have 1 microstate here. So total 7 microstates with energy 6 WH. So coming to the next, 5 WH. How many 5 WH are there? 1 and 2. So we have 3 5 here and 3 5 here. So we have 3 plus 3, 6 microstate with energy 5 WH. Next, 4 WH. 4 WH, how many we have? Only this. So 3 4 WH. Then 7 WH we have 1 2 here. So 3 and here 3. So 6 microstates for 7 WH internal energy. Coming to 8, we have only 3. There are no other 8s here. So 3 microstates with 8 WH internal energy. Then for 3 WH case, we have 1 microstate, and this already we counted. Then coming to 9, we have only 1 microstate. So what was the question? So question was, how many ways can the potential energy be 8 WH? So you have 8 WH here. We have 3 microstates for that. So there are 3 possible ways we are getting 8 WH internal energy. The answer will be 3. It's B. Right. So any questions regarding this problem? Then I assume all clear to everyone. Then coming to next question, we have for For that same system, in the above question, what value the potential energy will be have the maximum possible ways of occurrence. They are asking the maximum microstate, which state internal energy has the maximum microstates. We can check that. We have already calculated the microstates. So we see the 6WH case has 7 microstates. So this is the answer. So we have this. So question: what value of the potential energy will have the maximum possible ways of occurrence? That means which potential energy has the maximum microstates. So this is 6WH, right? So coming to the next question, consider as okay, let me stop it. Do anyone have any questions from the previous questions? Hello. Okay.
No, sir.
Okay.
No, sir. It's clear.
Okay. So coming to the next question, consider a staircase with 3 steps and 3 identical marbles arranged on them. The steps are of height h and marbles are weight w. How many ways the potential energy will be 6WH? We already did this kind of question. Let's check that. Same question I repeated, I think. Sorry. Same questions, okay. That's different. It's asking about potential energy 6WH. How many ways can the potential energy will be 6WH? Let's check. We have already calculated this. Right. Okay. Sorry. We are considering marbles now. Okay, sorry. It's not people. We are having marbles now. So the question is same. Just we will replace the peoples with marbles. We have 3 stairs, same thing of height h, 2h, and 3h. So we have 3 identical marbles now. They will look alike. So there is no need to arrange between themselves. So we will have a situation like this. This arrangement only we have. We no need to arrange between themselves because they are identical. So we will have the combinations like this one. So what is the question? How many ways the potential energy will be 6WH? 6WH will check. So we have 1 6WH here, 1 more here. So we have 2. So answer will be 2. Understood? Okay, coming to next question. For a system of marbles on an endless staircase, there can be cases of negative temperature. So as I have explained in the first question, if we have some limited number of energy states, like in this case let's assume we have limited staircase or limited marbles or limited people, then our entropy function is the number of microstates, let's let it as omega. Then this function will increase first, and at equilibrium it will be maximized, then after that it will decrease. So we need to check the temperature. This is inversely proportional to S, as you might mean, temperature formula is 1 over T is del S over del U, right? So temperature is del S. Temperature inverse is del S over del U. So U, we can write here, let's assume this variable as U, we can differentiate this. Then temperature is inversely proportional to this entropy. So if we do the derivative of this function, then we try to plot this in terms of temperature and U, we will see that this function will look like this. So this is 0 level, then this is positive, so some plus 2 plus 3, this axis is negative. So we see this is some number 5, so this is 5. So we see as entropy increases, temperature decreases, and at equilibrium this temperature becomes 0, and after that as entropy decreases, the temperature will also decreases like this. So it can go to negative temperature. I think sir already taught this kind of graph in his first lecture. So the question is, for a system of marbles of endless staircase, there can be cases of negative temperature. Endless staircase means the stair will be infinity. So how will the entropy will look like? As the staircase is not limited, so the entropy will increase monotonically as a function of some U or macro state. U is a macro state, so we can write omega is U. So we can see if the staircase are infinity, then this entropy will keep on increasing. Then in that case also, if we plot temperature versus U, then if we take the slope of this function, what we will get, as it is monotonically increasing, if we take the slope, the temperature is inversely proportional to del S over del T. So how will it look like? It's never 0. For a system of marbles on a endless staircase, there will be cases of negative temperature. So yes, it will go and it will stop something like this. clear the sound. So you need to calculate the slope of this function first. So let's see, it may not be as straight as this, but it will be increasing function. Let me draw this like this. It will be increasing. It may not be a straight line. So the point is, we have positive slope here, and the slope is changing. Then we need to calculate the temperature. Then it will be inverse of this. Then the temperature, as the slope increases, the temperature value will decrease. It will come like this, and when it reaches to infinity, then this point will come at meet at 0. Means the entropy goes to infinity. There will be, like, assume like there are some particles distributed in the vast space. There are some particles, they are distributed in a space. Then entropy increasing means what? Entropy between these states means they will collide with each other randomly, and their randomness will increase, and their separation will also increase. So at infinite time they will be vastly separated. One will be there like this. The temperature is like notion of temperature is like it's a collision between molecules or particles. It's an old notion. Like, what is temperature? Temperature is nothing but the kinetic term. Like, it's a collision between a byproduct of collision between the molecules in a block or whatever. Like in liquid, the collision between the molecules. In a solid, the vibrations between the vibrations in the molecule, something like that. So at infinite time, sorry, it's time and temperature, they are same, right? So infinite time there will be vastly separated and there won't be any motion. So in that case temperature will be absolute 0. If there is no motion, then temperature, there is no temperature. If there is no collision, there is no temperature. So okay, what is the question? Temperature can be negative or not? Okay, maybe I missed something. Okay, sorry. Please give me some time. I'll check this question and I'll tell you this in next class. Maybe I lost something in explaining these things. Okay, coming to the next question. Give me some time. I'll explain this question in next class. So the next question is, if the total energy of the system has upper bound and lower bound, the temperature is, okay, it's similar now. So we have upper bound and lower bound on the total energy. When this will happen? When we have some limited energy state, or in this case stairs, and limited marbles or limited people, then we can arrange them in a limited way. So in that manner we will have a upper bound, upper some maximum value for u, and we will have some minimum value for u. let's go to the previous example, then I can explain you. So you see, we have 3 stairs here and 3 people are here. So in this case we see we are getting a maximum potential energy and a minimum potential energy. So maximum potential energy and minimum potential energy means we have limited number of stairs and limited number of people. So in that case, how this will look like? If we have this U distribution, right, and we can calculate the entropy from the microstates. We have 6 microstates in this 6WH and 3 microstates in 5WH. Let's collect these first. How shall I collect this? We have okay, entropy is logarithm of microstates. So this corresponds to some specific internal energy. Then but yes, okay, let me go here. This is U, this is so my U starts from 3 WH. So let's this point be 3, 4, 5, 6, 9, and this axis is entropy. Then S is ln of microstates corresponding to certain U value. Then for 3 these U is in WH unit, so 3 means 3 WH. So how many 3 WH we have? We have 1, yeah. So the entropy will be ln of 1. Ln of 1 is 0. So for 3 case we have 0 entropy. So for similarly for 4 WH we don't have 4, okay. Then 5 WH, okay, we have 4. We have 4. We have 3 states with 4 WH. Yes. So entropy will be ln of 3. What is the value of ln 3? Let me check. Ln 3 is 1.09. So let's point this as 1 at 4. So it will be 1.09 somewhere here. So similarly for 5, how many we have? We have here 5 and we have 5 here. So 3 and 3, 6. We have 6, then ln 6. So ln 6 is 1.79. So for 5 it will be somewhere here 7. Sorry, it's going too far. 5 is 1.79. Then for 6 case we have 6 microstates here and 1 microstate here. No, sorry, not here. Here. So total 7 microstates. So for 6 case it will be ln of 7. Ln of 7 is 1.98. Let me rescale this, it's going too far. let me call this 2 and 1 is somewhere here. So for 4 we have 1.07, for 5 we have 1.79, and for 6 we have 1.94. Like it's ln 7, this is ln 6 value, and this is ln 3 value. So similarly we can check for 7 also. 7WH we have here and here. So 3 and 3, 6 again. So 6 ln 6 for 7 we have ln 6. So let's check for 8WH. 8WH we have here. So 3. For 8WH we have ln 3. This is ln 6. Only the last one remaining, 9WH. We have only 1 microstate. So ln 1 is 0. So if we connect these things, then we will see the behavior like this. So the entropy is increasing first, then at some point we can call it equilibrium point, it is maximum, then after that it is decreasing. So at this equilibrium point we have maximum number of microstates. The entropy is maximum at this point, and as we are going further, this entropy is decreasing. So what was the question? Okay, if the total energy of a system has a upper limit and lower limit, the temperature is okay. Okay, so for temperature 1 by T is del S over del U, as we are plotting over U. So if we can check this derivative function, then let me plot in 1 over T, then it will be easy for me to visualize this. Let's see. This is it. Okay, let me plot 1 over T. 1 over T is del S over del U. Then I can plot this in terms of U. So you can see in this region the slope is increasing. So my temperature, okay, now slope is increasing, then coming to flat. Okay. So this is maximum slope, then this is less slopey, this is less slopier than that. So we'll see, first it was more slopier, then the slope is decreasing. So first it was very slopey, then eventually the slope is decreasing, right? At this point the slope, if you will take the derivative at this point, you will see the slope will be 0. So it will be 0, as 1 over dt is del S over del U. You can do the derivative and you can check. The first at first slope was maximum, then slowly it is decreasing, and then it's coming to 0. So at first it is something, then it's decreasing, then it came to 0. Then coming to this side, then slope is decreasing, then it will go like this, then it got steeper but negative slope, so it will go like this, and at this point it will stop. So if I see this plot, this is 0, this is positive axis and this is negative axis. So I can see this temperature, this is positive for this part, and it becomes, as the entropy increases, the temperature is positive and the temperature it is decreasing, and at maximum entropy the temperature is 0. And after that, as we have limited states, so we can arrange them, and as this energy goes higher and higher, this entropy decreases. Then when this entropy decreases, the temperature is also decreases. So what we see, the behavior like this is actually temperature is not decreasing, as we are plotting 1 over t. Temperature is increasing, but 1 over t, this is decreasing. So effectively in this region temperature is increasing and 1 over t is decreasing, is negative there, means t is negative here, but this magnitude is increasing. See, -1, -2, -3, but magnitude is increasing, but it's negative. So what happens? So entropy increases, 1 over t decreases, that means t increases, temperature increases. So at maximum entropy, the temperature becomes 0. Then after that, this 1 over t is decreasing, that means t is increasing, but its magnitude is increasing, sign is negative. So in that sense, temperature increases from some value, then it comes to 0, then it goes to negative. Do anyone remember the plot for 1 over x? Anyone? As s increases, like this, asymptotic. So this behavior is like this. Okay, let's forget about it. Do anyone have doubts in this, whatever I have taught so far? Hello? Hello?
We are clear.
So coming to the question, so yeah, if you have upper bound and lower bound, the temperature it can go to absolute 0, and it is sometimes positive and sometimes negative. So B and C are correct. If the stairs are unlimited, then we can go internal energy up to infinity. So in that case, this is over U, it will go monotonically up, right? It won't show this behavior. Okay, coming to the next question. According to Boltzmann, entropy is what? So according to Boltzmann, entropy is function of the microstate, and it is related to the logarithm of this macrostate. This macrostate comprises of many microstates. So this entropy is proportional to exponential number of microstates. No, proportional to log of the number of microstate. Yes, it is extensive. Okay, extensive means uh, extensive and intensive property. Like if you change something in a system, like if you change the internal energy, then what will be the effect on this entropy? Like if you change um, temperature is an intensive property, pressure, number of particles, they are extensive. Like there are some particles here. Each particle has some energy, small u, let's say. Then if you increase the particle number of particles by some factors lambda, let's say I increase my particle to 2n, then what will happen? The total internal energy q, it will also increase because each particle has small u energy. So if you increase the number of particles, the total energy of the system also will increase. It will be 2u. So these macro states which are changing by change of this system. So that means scaling of the system, if it impacts the macro states, then it will be a extensive property. Like I am increasing the number of particles, then the internal energy also increasing by 2 factor, then it's an extensive property. But let's consider this small u. This is an the energy per particle. Let's say this small u is the energy per particle. This total energy divided by the total number of particles. Then if I include more particles in the system, then each particle has u energy. If I include more particles also, this u will be unimpacted. So it's not changing by changing. If I change the system, this u is not impacted. So u is a intensive property. But the entropy, this is some kb ln of some microstates. Let's assume I am increasing my particles numbers, then these microstates, they will also increase, right? So by changing the system, like by scaling the system, I am scaling here, I am adding more particles here, then microstates, it will also change. Then ultimately this entropy will be impacted, it will also change. If I include more particles, then this number of arrangements or the number of microstates, it will be more, so my entropy will increase. So it's changing by after changing my system. If I change my system, this entropy is changing. That means it's an extensive property. Sorry, yes, it's right. Entropy is such that for a gas in the microchemical ensemble, it depends on the total internal energy, volume, and chemical potential. For a gas in the microchemical ensemble, it depends. Okay, in a microcanonical ensemble, there is no exchange of heat or number of particles, so it's not a function of that. You can see it is dependent on the this microstates. For a microcanonical ensemble, for what is a microcanonical ensemble? In a microcanonical ensemble, the number of particles will be constant, and there won't be any heat transfer between these walls. So total internal energy will be constant. So as the particles are not passing, also number of particles constant, so chemical potential also be constant inside this system, and volume is also constant for microcanonical ensemble. So these things, they are not changing in the microcanonical ensemble. So if they are not changing, then the microstates, they will go some maximum entropy, and then they will stop. So after that, these parameters should be changing to impact the entropy more. So this is not true. Let me write it in a better way. So I have a microcanonical ensemble. So n is fixed and u is fixed. So there won't be any exchange of particles or energy. So chemical potential is also zero. Like chemical potential is the ability of this system to transfer particles. So as the particles are not changing, it's zero. So as these things are not changing, it won't impact the microstates much. Means for this set of variables, the microstates, it will be something like it will go like this. Microstates will go to some point, then it will stay, or it can't go beyond that. It's because these number of particles, I am not adding more particles though, so there won't be many collisions or something like that. I am not adding more energies, so there won't be any more collision between them. So the microstates, whatever they have, they can't go beyond certain limits. So if I am not adding more particles or more heat to the system, the entropy won't change. So for microcanonical ensemble, it won't depend on these things. So these two are correct. These two are wrong. Any doubt in this case? Are you able to understand this?
Yes.
Okay. Coming to the next question. Imagine there are 5 identical marbles on a staircase of infinitely many steps. So the steps, the energy states or steps, whatever you like to call them, they are infinity. They are like going on. Then we have only 5 marbles to arrange in these steps, and they are identical. And each step has energy, like each step has energy k equal to 1. This step has energy 1, this step has energy 2, this step has 3, 4, 5. And if I put a particle here, then its energy will be 3. In some arbitrary unit, we are considering only numbers in this question now. So if I put a particle here, its energy will be 4, here its energy will be 5, and so on. So imagine that there is a restriction that there can be no more than 2 marbles per step. Then for this system, entropy is maximum when the total and internal energy is okay. So as the numbers as the states are infinity, we have only 5 number of particles we can arrange between these things. So I can put some particles in each state here starting from 1, or I can put this particle in some 6th state or 7th state or something like that. I can only put 2 particles together, not more than that. So I can put these 5 particles in infinite number of energy states. So it's a chaotic system. Like I can put here, here, close to each other or very far from each other. 2 particles are there. Very close to, then 3 particles are there. So there will be uh, many possible ways of getting this. Like ultimately we need to calculate U, right? So U is summation of the energy of each state. So this is, as each state has uh, energy K, I can write this as K. K goes from 1 to infinity, and in each state maximum 2 particles can be there. So let me define a function uh, theta, and this function theta can have value 0, 1 or 2, no, not more than that. So K goes from 1 to infinity, this is K theta. So for some cases, like let's calculate for 5 internal energy U. So how can I get 5? I can put 2 here. I can't actually get 5. There will be minimum. Let's check first what is the minimum energy we can get in this system. I can put maximum 2 particles in a state. So in the minimum state I am putting 2 particles with energy 1. So there will be 2 particles. Then I can put 2 particles here, then 1 particle here. This is the minimum I can do for a system. So what will be the internal energy for this case? This energy state's energy is 1. This energy state's energy is 2. This energy state's energy is 3. So what will be the internal energy? There are 2 particles. So 2 into 1, plus there are 2 particles here, 2 into 2, plus there is 1 particle here, 1 into 3. So what will be the internal energy? 2 plus 4 plus 3, it's 9. So I can get 9 internal energy minimum. Okay, so then I have to check the above value. Like let's check for internal energy. Let's say there is an or some, let's say 12. How many ways I can get 12 internal energy? Means the value of 12, how many ways I can get? So I can have 3 here, I have 4, 7, I need more 5, then 4 and 5. I need to put 1 and put here, then I shift this here. Or shift this. what I'm trying to explain is, like, I'm not getting the exact example to explain. Let's get some internal energy 15. That means how many ways I can get 15. I can get 15 like there are I can write this 1 plus 1 plus 2 plus 2 plus 3. How much I'm getting. So let's forget about putting two balls in each state. Let's talk about the partition function. Partition function means this 15. How many ways I can write? I can get 15 here. So I can write 1 plus 1 plus 1 plus 15 times 1. This is one case. Or 2 plus 1 plus 3 plus something like this. I'll get something which will give me 15. Then 3 plus 1 plus 1 plus 1 something like this, it will give. So you can see there are some limited number of ways I can write 15. So there are more than one way I can write. I can get 15 by adding this number. So if I go higher 17, then there will be more number of ways I can get 17. If I go higher like 100, then there will be some more number of ways I can get this 100. So the point is the number of ways I can get this partition function is the microstate I need to calculate. So entropy is ln of omega. So as the internal energy increases, the microstates will increase. That means the number of ways I can get that number is 100. Let's say it will be more than the number of ways I can get 15. So as I increase u, the number of microstate it will also increase, right? Then as this staircase are going to infinity, in the case of infinity I'll have microstates also approaching to infinity. So in that case my entropy will be maximum when this internal energy goes high and high. So in this case the entropy is maximum when the total internal energy is going to infinity, right? Did you understand this, or shall I explain it in some simpler ways? Hello? Can someone confirm that they got it? Hello?
Okay.
Okay. You got the idea about partition function, right?
Yes.
Okay. Like this is the staircase, like how many ways I can write 15, and this is the total energy of that system. How many ways I can arrange my marbles so that I will get 15. There are some limited number of ways I can get this 15. If I increase the u value, then the number of ways I will get this u value will be increased. Right. Okay, so coming to the next question. The possible values for the energies of a system, the above question are okay. So we calculated the minimum energy state for the above question. Right? in the above question we could put two marbles.
Sir, once again, tell me the answer of the above question, sir.
Okay, for the above question the answer is infinity.
Oh, okay. Okay, sir.
Yeah, you see, as this value u is increasing, my
Okay.
microstates they are increasing. So as u going to infinity, this microstate will also tend to infinity, so that my entropy will also increase. I'll have maximum entropy at u tends to infinity.
Okay, sir. Thank you.
So in the above question, uh, we are allowed to put two marbles in a single stair. So I can put maximum two marbles here, then two here, and one there. For this system, how much energy I am getting? I am getting 2, and here 2 into 2, here 1 into 3. So I am getting 2 plus 4 plus 3. 2 plus 4 plus 3 is 9. So from these options I see 5 and 6 they are not allowed. 1 and 0 they are not allowed. So I have minimum energy 9. So the possible value of energies of the system in the question is this one. Since my minimum energy is starting from 9, then I can do one thing, like I can put this ball and marble in the third state, I can put this in fourth state, then my energy will be 10. If this 3 is going to 4, then my energy will be going to 10. Then if I put that same marble in fifth state, then my energy will go to 11. So correct way is this one. This is also correct in some sense, but it's not including the minimum energy. So this is more correct. Eventually this sequence will reach this sequence. So fundamentally this is the correct answer. Okay, so I have this many questions for this session. Do anyone have some doubts from these questions or some other doubts from the
So
classes?
which one is the correct answer for this one?
The first one. This D is also a correct one, but it does not include 9 and 10.
9 and 10. Okay, okay.
Yeah. So this is correct actually. So I have this many questions for this session. Do anyone have any doubts from these questions or anything from the class that sir has taught? We can discuss. We have still 15 minutes. So you guys have some idea about programming, right? Any programming, Python or Mathematica or C? Hello? How many of you know programming? Hello? I assume then no one knows programming. Okay. If you know something programming like this, then you can like plot these things in using some programming for some large values, and you can check their behavior. Like it's very hard to compute them manually. Like if the number of steps are small, a number of particles are limited, then it's very convenient to calculate these functions. But as we are including more particles or more energy states, it is becoming hard to compute. If you know some little bit of programming, then it will be very easy to visualize these functions. Okay, then Do anyone have any questions from this these sets? Like for the first question, the entropy is always increasing and it will reach to. Okay. So for the first question, the entropy will increase and it will reach to a maxima at equilibrium. The first question's answer is B. Second, a macrostate is typically corresponds to huge number of microstates. And we have calculated this by hand. It is getting at around 18.95. And then we have calculated the entropy for Bob and Alice also, and we got higher number of entropy for Alice, like 15.72. Then we did this staircase problem for 8 WH internal energy states. There are 3 microstates. You guys understood, right, how to compute these things, because they are very general. So if these kind of questions you are getting, different questions but similar format, you can do, right? You just have to arrange them or in all possible ways, and then the number of ways each state is corresponding, then that number you have to plug in the logarithm function, then we will get the entropy for that corresponding internal energy. Then you saw, like, if the things that we are arranging, like people, they are very distinguishable. So for each combination also we will have many number of arrangements for if they are distinguishable. But if we are taking them to be very indistinguishable, then that means we can't distinguish between this person and another person, then there is no need of arranging between themselves. So in that case we do not have this kind of arrangement. We will have some combinations, like placing the persons of marbles. Like marbles are indistinguishable, we can put those marbles in these combinations and we can compute the internal energies and we can compute the entropy. If they are distinguishable, like if I say in the physics term, the bosons and fermions, they'll always look alike. Like one electron, whatever it will always be same kind of electron what is there. You can't distinguish between electrons because they look alike. Similarly bosons also, the only difference between them is that you can put any number of bosons in a single energy state, but you can't put any number of fermions in a single state, because Pauli exclusion principle forbids that. We can only put one fermion at one energy level, and we can put any number of bosons in a single energy state. So these will be having applications in particle physics, like bosons and fermions case. You can arrange bosons and fermions and you can calculate what will be the minimum energy for boson case and for fermion case. Like if you have energy levels like this, like let's consider quantum mechanics. The minimum energy will be half h cross omega. Let's assume for simple harmonic case, then 3 plus 2 h cross omega, something like this, and this will go. if they are bosons, then you can, if you have four bosons, you can put them four bosons in the lowest energy state, and your total energy will be 2h cross omega. But if you have fermions, then you can't put two fermions together. You have to put one fermion in one energy state. So will be bound to put them in different energy cells. So in this case, the minimum internal energy will be very different than this boson case. It is half equals to h cross. It will be more than this 2h cross omega. That's the difference. We will be seeing these applications in quantum mechanics and statistical mechanics in the next upcoming classes. And you see, if we have limited number of energy states or limited number of things to put on these energy states, or things by things, I mean, if you have limited number of particles to put on these energy states, the behavior of entropy, it increases first, and at equilibrium the entropy goes to maxima, then after that it decreases. Entropy, if a system increases equilibrium, it normally does not go beyond that. It tries to stay beyond at that point. If you want to change this internal energy, then you have to put additional extra catalyst from outside. Then it will, you are manually distorting that system, deviating from this equilibrium. And in that case, if you are trying to increase the internal energy by putting some additional external force or external energy, in that case this entropy will decrease. And depending on this entropy, the temperature of the system will also vary, as this is inversely proportional. The temperature is inversely proportional to the variation of entropy. So it will behave inversely as a slope of entropy. So in these also we already calculated. Here we consider the identical marble case. Instead of people, we considered identical marbles, so we don't have to arrange between themselves. So, and this question, give me some time, I'll clarify this and I'll give you an answer in the next class. Okay, the Boltzmann law, you know, Kb log ln of this microstate, and this entropy is a extensive property. And these things we already saw. Okay, if you don't have any questions, we can stop here. Okay, then see you in next Saturday. You can leave.